Hello, class, and welcome to Chapter 2, Section 3, which will be on elements and compounds. So we're starting to get a little bit more into what makes up chemistry, specifically looking at elements and compounds. Let's talk about what a pure substance is first. A pure substance has matter that has a uniform and definite composition, and every sample that we were to take from a pure substance would be exactly the same. Pure substances have definite properties and are made of one type of atom, and this is what we call an element. So examples are iron, gold, and oxygen. And if we take two or more types of atoms, we create a compound. And this is really important. So I'm just going to restate that again. Pure substances are made up of one type of atom, and we call those elements, like iron, gold, and oxygen. Those are the elements in the periodic table that we'll talk about. But if we put two or more types of atoms together, then we form a compound, like salt, sugar, or water. So salt is sodium chloride, NaCl. Sugar can be glucose or fructose, lots of different atoms combined, like carbon, hydrogen, and oxygen in ratios that come together to form glucose. And then water is H2O. So I'm going to say it one more time. An element has one type of atom, and that's like iron, gold, or oxygen. And we have elements listed in the periodic table. But if we take two or more types of atoms together, we get a compound. So we have sodium chloride is salt or table salt that combines sodium with the abbreviation Na and chloride with the abbreviation Cl. And then water is made up of two hydrogen. So we put H2 for two hydrogen and then an oxygen. So those are examples of compounds. Substances, elements then. So we're now talking about elements, which have just one type of atom in them. Substances are substances that cannot be broken down. So elements are made up of all of the same atoms. So here we have hydrogen with an atomic number of 1, an atomic mass shown there. This is the atomic symbol of hydrogen, a big letter H. We have nitrogen with the atomic symbol of the uppercase N, and lead with the atomic symbol of Pb. So those are types of elements. These are substances that cannot be broken down, and they are made up of all of the same atoms. And here are examples: hydrogen, nitrogen, and lead. Monatomic elements are composed of single atoms not bonded to each other. So for example, sodium is an example of a monatomic element, a single atom not bonded to each other. So an example of a monatomic element is sodium. The prefix mono means like one. A diatomic element, di is the prefix meaning two, and these are elements that contain two of the same elements bonded together. So for example, hydrogen is usually always bound to another hydrogen molecule. As shown here, each circle represents a hydrogen atom, and a diatomic element means there's two atoms bound together to form that element. So hydrogen H2 is an example of a diatomic element. More about diatomic elements. They're elements that exist as diatomic molecules, and you should know these or memorize. We have bromine, iodine, nitrogen, chloride, fluorine, oxygen, and hydrogen. So it's a good idea to memorize these diatomic elements, which again are elements that exist with two of the same elements bound together. So bromine we would write as Br2 because we would show those two bromine atoms bonded together. Hydrogen we would write as H2 to show those two hydrogen atoms bound together. Iodine and oxygen. So a good idea to memorize those diatomic elements. There are 7 diatomic molecules, and they are all highlighted here for you. Nitrogen is atomic number 7, and then the 6 atoms, or nitrogen, oxygen, fluorine, chloride, bromine, and iodine form a 7 on the table, and that leaves 1 more, and hydrogen is atomic number 1. So this is a little kind of easy way to remember these diatomic elements listed in the diatomic or in the periodic table. They form another number 7, and then we see hydrogen over here. So we have the 6, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. This forms the number 7. To remind you that there are 7 diatomic molecules. We have 6 of them listed here, and the 7th is hydrogen. So hopefully that helps you, serves as a little memory trick to remember the diatomic elements or molecules because they're 2 atoms put together, and then where they're located on the periodic table. All right, so then we talked about elements, monatomic and diatomic elements. Let's talk about compounds. Compounds are made up of 2 or more different atoms chemically combined. They have a fixed composition, and they can be separated, usually due via a chemical process, back into simpler substances. So for example, we have CO2 shown here with these 2 drawings. We have 1 carbon atom in the middle. So the black is the carbon atom in the middle. On the right side, it's this little gray circle. And then the 2 oxygen molecules are coming out in a linear way. So carbon dioxide shape is really important to compounds. And carbon dioxide makes a linear shape, meaning it's nice and linear and straight across. We'll get into other shapes of other compounds, but some compounds have bends in between the bonds due to charges that are reflecting each other or pushing the atoms away from each other. But carbon dioxide has a linear shape to it, meaning that the atoms are nicely put in a row. So that's carbon dioxide, an example of a compound made up of 2 or more different atoms, chemically combined, having a fixed composition, but could be separated chemically back into 2 oxygen and 1 carbon. Breaking down compounds. So how do we actually break down compounds or put compounds together? A chemical change is a change that produces matter with a different composition than the original matter. So for example, whenever we go through a chemical change, what we produce will be totally different than what we started with. It's kind of like being in your kitchen and taking ingredients and making something at the end. The same type of idea is what we work with when we talk about chemical changes. So again, a chemical change is a change that produces matter that is totally different in composition than the original matter. So if we take our sugar, our compound, and again, a sugar is a name for many different types of sugars. We have glucose, which is a simple sugar, which is probably the most common, that's C6H, H12O6. And then if we break down sugar or glucose, we're breaking it down into products that will have different compositions. So through the process of heat, we could burn sugar and give off carbon and water. Then if we take that water and use electricity, we can break water down into its individual components of hydrogen and oxygen. Properties of compounds. The properties of compounds are different from the properties of the elements that make up the compound. So even though a compound is made up of 2 or more different elements, the properties of that compound, like carbon dioxide or table salt or sugar, will be totally different from the glucose, hydrogen, oxygen, sodium, chloride that make up those elements. For example, if we take table salt, which is sodium chloride, NaCl, that is our compound. It's a harmless white solid that many of you have probably eaten 10 or 12 times today. But if we break it down to its individual elements, like sodium, which is the element, it's a soft gray metal by itself. And chlorine, which is a diatomic element, is another element, and that's a pale yellow, very toxic gas. So just take for a moment and appreciate the complexity of chemistry and how God designed our world. Table salt we eat every day. And if you eat too much table salt, that is not good for you. It'll lead to high blood pressure and other problems. But if we break the compound of table salt down into sodium and chloride, we can't eat sodium. That's a soft gray metal. And you certainly never want to breathe in chlorine because it's a pale yellow toxic gas. But when you combine them, you can eat them and it makes your food tasty. Distinguishing then between a pure substance and a pure mixture, you can kind of use this table and flow chart to help you with this. When you look at matter, ask yourself, can the matter be physically separated? If it can be, then we're talking about a mixture. If the matter cannot be physically separated, then that is a pure substance. Going back to mixtures, if the composition is uniform, that's a homogeneous mixture, which is what we term as a solution, where you can dissolve the solutes into that liquid. That would be a homogeneous mixture or solution. If the composition is not uniform, that is a heterogeneous mixture, meaning you cannot separate the parts of that mixture, or you cannot combine the parts of that mixture together. A pure substance cannot be physically separated. Can it be chemically decomposed? If it's yes, then that's a compound. So if we have table salt, for example, if we can chemically decompose table salt, that's a compound. But if we cannot chemically decompose it, that would be an element like oxygen, hydrogen, nitrogen, sodium, or chlorine by itself. So let's go through a sample problem classifying materials. So when a certain blue-green solid is heated, a colorless gas and a black solid form. All three materials are substances. Is it possible to classify these substances as an element or a compound? Let's use our steps and analyze the problem, and then we'll solve it. We know that a compound is made up of two or more elements that are chemically combined. Let's identify the relevant concepts. A compound can be broken down into simpler substances chemically by a chemical change, but an element cannot. Heating can cause a chemical change. So we know it's a compound because it's made of two or more elements that are chemically combined. Then we solve. List the known facts and the relative concepts of the problem. We know that a blue-green solid is heated. We'll determine if the substance are elements or compounds. A colorless gas and a black solid will appear. Before heating, remember there was one substance, and then after heating, we're getting a colorless gas and a black solid. So after heating, we're getting two substances. So we're going from one substance to two substances. That's a chemical change. The blue-green solid then must be a compound because we're starting with one substance and we're breaking it down into its two elemental components. So the green solid must be a compound because when we put it through a chemical change, the heating process, we get a colorless gas and a black solid appearing. So we know the colorless gas and the black solid are pieces or elements of the compound that we started with. We cannot determine, we don't have enough information to determine if the colorless gas and the black solid are elements or compounds based on the information given. If they would take us through another experiment and we would take that colorless gas and a black solid and then try to chemically break it down again, we could determine if the colorless gas was a compound, if we could break it down into more parts, or if the solid was a compound. But from the information given, all we know is that we started with a compound, which was the blue-green solid, and we were able, through a chemical change, the heating process, breaking it apart into two more pieces, the colorless gas and the black solid. From there, we would have to go through another experiment to determine if that gas and solid could be broken down into more pieces. Symbols and formulas. This is where chemistry is like another language to learn, which makes it fun. Chemists will use chemical symbols to represent the elements, and chemical formulas to represent compounds. And what do we mean by that? Let's talk about this. Using symbols to represent matter is not a new idea by any means. If we go back, alchemists used symbols like the ones below to represent elements. Isn't this fun to see the original alchemists' symbols? Specifically, these are some of Dalton's symbols as well. Alchemists and John Dalton, which was an English chemist, kind of in the late early 1800s, used drawings to represent chemical elements. So this is nothing new to use a symbol or a drawing to represent some of these elements. More about symbols and formulas, we have Berzelius, who was a Swedish chemist, kind of around the same time frame, based the symbols on Latin names of the elements. So he got down to the Latin roots of the elements, and each element is represented by a 1 or 2 letter chemical symbol. The first letters of chemical symbols are always capitalized, and if there is a second letter, it is lowercase. And you'll notice there's a little chemical symbol from a teacher, MC, who I have borrowed some of her PowerPoints from. So you'll notice her chemical symbol, which is not a true atomic symbol, is on the right of all these slides. But these chemical symbols, again, will be either 1 or 2 letter, usually from Latin names or roots. The first letter will always be capitalized, and the second will always be lowercase. Some of the Latin names and the English names are the same, so the element symbols do not change, but some of the element names are different in English, so their symbols will not match. Examples are sodium, which has the chemical symbol Na. The Latin name is natrium, so that's where the symbol Na comes from sodium, because sodium's Latin name or Latin root is natrium. Copper, chemical symbol is Cu, and that's because the Latin name for copper is cuprum. So just keep that in mind. Sometimes the chemical symbols don't always match with the element name, because some will use their Latin names for the chemical symbols. So here's a look at symbols and formulas in the periodic table, specifically ones that don't completely match the chemical symbol with the English name. And you can see the Latin name and where it would get the symbol from. So sodium, potassium, antimony, copper, gold, silver, iron, lead, and tin. These are a few of the most common that you should really take to heart and memorize, and look for a potential quiz on symbols and their English and Latin names in the future to help you with that. Chemical formulas then is a shorthand way to represent chemical compounds. So again, a compound is taking 2 or more elements together, and a chemical formula will be a shorthand way to represent that. We use the element symbols and then the numerical subscripts, which will tell us the number of each element that will be required. It'll tell you how many of each element there is in the compound. So example, water is a compound that's made up of 2 hydrogen and 1 oxygen. So you never include the number 1. So if there's no number, if there's no subscript after the symbol, that just means there's 1. But if there's a number greater than 1, then that'll tell you the number of elements in that compound. Glucose has 6 carbon, 12 hydrogens, and 6 oxygen. And glucose, again, is a simple sugar, the most common. Then the periodic table. All of the known elements are separated and organized into groups based on a set of repeating properties. And the periodic table allows you to compare the properties of one element or a group of elements in a column to another element or a group of elements. So each element in the periodic table is identified by its symbol placed in a square, and a group of elements refers to a column of elements. That is a specific group. The periodic table, all of the elements are listed in order of their atomic number, and the atomic number is unique for each element. There are 7 periods, which refer to the horizontal rows on the periodic table, and the properties of the elements will vary as you move across a period. The vertical columns are called groups and either have an A or a B next to it. So again, if we go back, the horizontal rows are called periods, and the vertical kind of columns are called groups. And you can see each vertical column has an A or a B next to it. So just keep that in mind. Elements within the same group will have similar chemical and physical properties, and we'll go more into the periodic table as we move forward in this course. Thank you for listening, guys, and take care.